My name is Jamil, and today in this section we'll be looking at graphs of basic functions and the symmetry that's involved with them. Let's take a look at our objectives. First objective is to learn about continuity, then increasing and decreasing functions, the identity function, the squaring function and symmetry with respect to the y-axis, the cubing function and symmetry with respect to the origin, the square root and the cube root function, the relation x equals y squared and symmetry with respect to the x-axis, and then finally even and odd functions. We're going to start off by introducing the concept of continuity. Now, the formal concept of continuity isn't something that you get to until you take a calculus course, but for our purposes we'll define continuity in the following way. A function is continuous if we can draw it without lifting our pencil up off the paper. Let's look at some of these examples and determine where their intervals of continuity are. Here we're asked to find out what the intervals of continuity are. Here we're asked to find the domain over which these functions are continuous. Now, since we can draw this graph from the beginning to the end without ever lifting up our pen off the paper, the interval of continuity for this particular function would be negative infinity to infinity. For this next function, you may notice that there's a hole in the graph here located at the x equals 3. So we would say that our interval of continuity is from negative infinity to positive 3, not including either, and then from positive 3 all the way to infinity, again, not including the 3. So that way there's a hole in the graph. Let's look at another example. Here in this function, when we're asked to find out where the domain of continuity is, we would say that this function is continuous from negative infinity all the way until this break in the function, which occurs at x equals negative 2. So our first domain is from negative infinity to negative 2, and we don't include the negative 2 in this case. And then it's continuous again starting after the negative 2 going all the way to infinity. So again, don't include the negative 2, but go from negative 2 to infinity on this side. Another important concept to discuss is that of increasing and decreasing. We say that a function is increasing if it rises over its domain, or the function is decreasing if it falls over its domain. Let's take a look at some more specific definitions of this. Criteria for increasing, decreasing, and constant. Suppose that a function f is defined over the interval I. F increases on I if, whenever x1 is less than x2, f of x1 is less than f of x2, and f decreases on I if, whenever x1 is less than x2, f of x1 is greater than f of x2, and then f is constant on the interval I if, for every x1 and x2, f of x1 is equal to f of x2. Let's go ahead and take a look at some examples that involve us finding increasing, decreasing, range, and domain. Here we're asked to determine the intervals of the domain over which the following function is first increasing, then decreasing, then constant, and then after that we're to give the domain and range of the function. So here's a picture of the function that we've been given. We're first asked to find out where this function is increasing. Now you can see from looking at this that the function is falling in this region, constant here, and falling again there. So there are no intervals over which this function is increasing. Now to find out where this function is decreasing, we see that it continues on to negative infinity. So all the way from negative infinity to the x value negative 2, this function is decreasing on this side. So that's from negative infinity to negative 2. And then if we look on the other side, we see that it starts to decrease again at the x value 3 and continues decreasing all the way to infinity. So it also decreases over the interval from 3 to infinity. Now, as for where this function is constant, you can see that the function has the same f of x values for all the x values between here and here. So it's constant over the interval from x equals negative 2, from x is equal to negative 2 to x equals 3, but we can't include the negative 2 or the 3 because no point exists there. Now in finding the domain, we can look at this graph and see that every x value on the x-axis has an f of x value associated with it. So the domain for this function would go from negative infinity all the way to infinity. And now finding the range of this function, what we need to do is look at the y values that the function comes across, and we can see here that it goes all the way up to the y value infinity and comes down to the y value 2, and then it jumps to the y value 1.5 and falls all the way to the y value that goes to negative infinity. So our range here would be from negative infinity to 1.5, and then again from the y value 2 all the way to infinity. Now what we need to do is take a look at some of our more basic functions. The first function that we want to talk about is the identity function. It's given by the equation f of x equals x. So for whatever input of x we put into this function, we'll return with the same value as the output. Let's take a look at a graph of f of x equals x. You can see that this function is a linear function with a slope of 1 and a y-intercept of 0. Its domain is from negative infinity to infinity because it uses all the x values on the x-axis, and likewise its range is from negative infinity to infinity because it uses all of the y values on the y-axis. If we look at the intervals where it's increasing, it's always increasing, so from negative infinity to infinity, this function is increasing, and likewise it's always continuous since there are no breaks in this particular function. The next function we want to look at is called the squaring function. Its equation is given as f of x equals x squared. Here you see a graph of f of x equals x squared, and what we're going to do now is go through the same criteria and look at where it's increasing, decreasing, and continuous and such. So for the interval of continuity, or let's start with the domain actually, the domain here is from negative infinity to infinity because it uses all the x values on the x-axis. The range, however, has a minimum value. The lowest y value that we'll get is the y value y equals 0, and then it will continue all the way up. So the range for this particular function is y goes from 0 all the way to infinity, and we need to include the 0 on this one. As far as increasing goes, the interval of increasing is from 0 all the way to infinity. The interval of decreasing is from negative infinity all the way to 0, and it's continuous all along its domain. You may notice that if we were to take this graph and fold it in half along the y-axis, we have what would be considered mirror images. This is called symmetry around the y-axis, and we're going to define that right now a little bit clearer. Symmetry with respect to the y-axis. If a function f is defined so that f of negative x is equal to f of x for all x in its domain, then the graph of f is symmetric with respect to the y-axis. The next function we want to look at is the cubing function. The cubing function has the equation f of x equals x cubed, and we'll take a look at the graph of that now. Here you see the basic cubing function. The domain of this function is all real numbers from negative infinity to infinity. Likewise, the range is also from negative infinity to infinity on the y. If we ask about where it's increasing, the cubing function is increasing all the way from negative infinity to infinity. It increases everywhere along its domain. So as to where it decreases, the answer would be it has no intervals in which it decreases. Continuity for this function, again, it's continuous all the way from negative infinity to infinity. If we were to talk about symmetry for this particular function, we could fold the graph along the y-axis and then flip it over the x-axis, and then you would see that this branch of x cubed would actually overlay perfectly on top of this branch of x cubed. This type of symmetry is called symmetry with respect to the origin, and we'll define that a little clearer now. Symmetry with respect to the origin. If a function f is defined so that f of negative x is equal to negative f of x for all x in its domain, then the graph of f is symmetric with respect to the origin. Let's take a look at some examples where we're asked to find and determine the symmetry of these functions. Here it says, use the analytic method to determine whether the graph of the given function is symmetric with respect to the y-axis, symmetric with respect to the origin, or neither. Now we're given the function f of x equals negative x cubed plus 2x. So what we need to do in order to determine this is see what happens to our function when we input a negative x value. So rewriting our function, f of an input, and we'll leave parentheses as placeholders. And now inputting in a negative x to see what happens, f of negative x is equal to negative, and then negative x cubed plus 2 times negative x. Working with this, we have negative x cubed, which means a negative times itself 3 times, so the result is negative x cubed without parentheses. But since there's a negative in front of it, the negatives work together to form a positive, since we have a total of 4 negatives here altogether, and that would become positive x cubed. And then 2 times negative x ends up being negative 2x. So now this function doesn't look exactly like the function we started with. However, we can go ahead and factor out a negative from this. And when we do that, we have negative x cubed plus 2x. And then we realize that what's in parentheses here is actually the original function we started with. So this is equal to negative f of x. So that satisfies the criteria for symmetry with respect to the origin because f of negative x is equal to negative f of x. Why don't you take a few minutes to try this next example on your own. Please use the analytic method to determine whether the graph of the given function is symmetric with respect to the y-axis, symmetric with respect to the origin, or neither. The function you're given is f of x equals 0.5 x to the fourth minus 2x squared plus 1. Go ahead and give this a try. Check back with me when you've completed it. Okay, let's see how you did. Your function that you were given was f of x equals 0.5 x to the fourth minus 2x squared plus 1. And again, what we want to do is we want to write this function, leaving a space for our input. So I'll use parentheses again as a placeholder. So that's going to give us the following skeleton equation. And now what I want to do is I want to replace a negative x in each of these parentheses to determine what kind of symmetry it has, if it possesses any at all. So now going back and working this out, negative x raised to the fourth, well, a negative raised to an even power becomes positive, so this ultimately ends up as 0.5 x to the fourth. Likewise, this negative x, since it's being squared, ends up being a positive x squared. So the sign stays negative 2, and then we get the positive x squared, and then plus 1. And now if we compare this to our original function, we see it's identical to the original f of x. So this is equal to f of x. So by going through this exercise, we've shown that f of negative x equals f of x. And what that means is we have symmetry with respect to the y-axis. The next function we need to look at in our basic graphs is the function f of x equals the square root of x. So here I've drawn for you this function f of x equals square root of x. Its domain, you may notice, is not all real numbers in this case. The domain starts here at the origin, or x equals 0, and continues to infinity. So the domain is from including 0 all the way to infinity. The range of this particular function, again, the y values, the lowest y value we find is at 0, and then it continues upward to infinity. So our range is from 0 to infinity, including the 0. As far as the increasing goes, you can see that's increasing on its entire domain from 0 all the way to infinity, which means there's no place on its domain where it's decreasing, so there is no decreasing section of this. And as long as the graph exists, it is continuous, so it's continuous throughout its entire domain, starting at 0 and going all the way to infinity. Let's look at our next basic graph. This is the function f of x equals the cube root of x, and unlike the square root function we just saw, every real number does have a cube root, so you can see that its domain is from negative infinity to infinity. This graph does continue upward all the way to infinity and down to negative infinity on the y, so our range is also negative infinity to infinity. It's increasing the entire way, so from negative infinity to infinity it's increasing. That means there's no intervals of decreasing for this particular graph. And as far as continuity goes, again, we can draw the whole thing without lifting up our pen, so it's continuous from negative infinity all the way to infinity. Now, one of the things you may recall about a function is that for every function, for every input, there's only one output. Some relationships that we look at are not functions, but we might want to treat them as functions. So what we're going to do now is look at how to handle these types of situations. The most common equation that this is seen in is x equals y squared. So here we have x equals y squared, and what we want to do is solve this equation for y. So rewriting it as y squared equals x, and then taking the square root of both sides, we get that y equals plus or minus the square root of x. And what that means is we really have two completely separate functions. We have y equals the positive root of x, and we have y equals the negative square root of x. Now these two separate functions, when combined, result in our original equation. Now if we were to fold this relationship along the x-axis, what we would see is that the two halves would coincide exactly. So this gives us a third type of symmetry. We call this symmetry with respect to the x-axis. Let's go ahead and define that a little more formally now. Symmetry with respect to the x-axis. If replacing y with negative y in an equation results in the same equation, then the graph is said to be symmetric with respect to the x-axis. So the last two terms we need to look at in this section are even and odd. A function is said to be even if it's symmetrical with respect to the y-axis, and a function is said to be odd if it's symmetrical with respect to the origin. Let's go ahead and take a look at a couple of examples and determine whether or not they're even, odd, or neither. Here we're asked to decide whether each function is even, odd, or neither. And in the first one, we have f of x equals 8x to the fourth minus 3x squared. And in the second one, we have f of x equals 3x squared plus 5x. So we'll start by taking this function, 8x to the fourth minus 3x squared, and we'll rewrite it, leaving it in parentheses as our input. So we've got 8 parentheses raised to the fourth minus 3 parentheses squared. And what we'll do again is we'll replace these with negative x's in an attempt to try to determine what type of symmetry they have. So now, because we have a negative being raised to a fourth power, that's going to result in a positive. So this is actually going to end up being 8x to the fourth. And we've got a negative 3 here, and a negative x being raised to an even power. So the negative x becomes a positive x squared, but with the negative 3 in front, it's negative 3x squared. Now comparing this to the original equation, we see it's identical. So we've got f of x here, and what we've shown in this particular problem is that f of negative x is equal to f of x, and that results in symmetry with respect to the y-axis. So this function is said to be even. In the next example, we were given that f of x equals 3x squared plus 5x, and again we're asked to find if it's even, odd, or neither. So we'll go about it the same way, leaving space for an input of negative x. I'll rewrite the equation and then substitute in negative x. And now, working this out, negative x raised to the second power ends up being positive x squared. So the first part is 3x squared. Then positive 5 times a negative x to the first power ends up being a negative 5x. So we have 3x squared minus 5x. Now this function is not identical to the function we started with, so it's not even. You might think we could factor out a negative to try and make it match up, but in doing so, we can't do it either, because when we try that, we pull out the negative, we get negative 3x squared plus 5x, and what's inside doesn't match up either. So this is not equal to the original function f of x, nor is it equal to the original function with a negative in front of it. So it's got no type of symmetry, so it's not even or odd. In this section, what we've done is look at some of the basic graphs and the symmetry that they possess. You should continue to practice by doing the exercises in your textbook, and I'll see you next time.